structure of the outer parts of neutron stars. But I know you're not all astronomers in here, so I will remind those non-astronomers about neutron stars briefly before talking about how we can view neutron stars and figure out what's going on in terms of their structure by looking at those neutron stars that get heated up by accretion onto the surface. I'll show what we've observed in a number of these objects now. We can actually see the crust cooling down and talk about what sort of constraints that can put on the structure of the crust of the neutron star. And then spend a little bit of time at the end talking about one complicating issue, which is that accretion doesn't totally shut off in quiescence, and what that can tell us, or what a problem that might actually be. So very briefly, why do we care about neutron stars? Of course, these are one possible outcome of stellar evolution. These are typically have a mass of around about 1.4 solar masses and radii of 10 to 15 kilometers. And so average density of these objects is sort of around about 10 to 15 grams per centimeter cubed. And they're certainly several times above nuclear saturation density in the core. The gravitational redshift on the surface is around about 0.3. And so these are extreme in basically every property they have. And they're really an astrophysical lab for the densest directly observable matter in the universe. So the structure of neutron stars is kind of interesting. It's quite different from basically any other type of star. In the core, where you have the highest densities, is where the structure is least known, right? And so these are where the structure there depends on the strong interaction at much greater than nuclear density. And the density dependence of many of the key parameters that go into calculating what should happen here are not well known. And so the structure at the center is very unknown. This talk is mostly, though, going to be about the outer part of the neutron star. So the outermost part of the neutron star, you get an atmosphere. The atmosphere of the neutron star is relatively small. It's about a centimeter or so, or a few millimeters thick. And the objects I'm talking about, these are typically hydrogen atmospheres. The heavier elements sink very rapidly down into the star because of the strong gravitational field. As you go down, you can have an ocean on the surface, and that then will freeze and solidify into a crust. So these are the only stars that have a solid surface. And that crust is typically a few hundred meters deep or so. And this is caused by the nuclei being forced into a lattice structure, giving you a solid surface. As you go down into the neutron star, as the densities increase, the neutrons prefer not to be in the nuclei, and you end up with a higher and higher fraction of neutrons compared to protons and electrons, and the nuclei break down. And in the center is where you think we have mostly neutrons, or it could be something completely different. So where do neutron stars, what sort of part of the phase space do neutron stars probe? If this is temperature density or temperature chemical potential, neutron stars hit this low temperature, high density or high chemical potential area that you don't probe in particle accelerators, where you look at much higher temperatures. But in the crust of the neutron star, the densities are lower, and actually the sort of science that EFRIB will be able to do will actually start to probe some of the properties that you actually have in the crust in neutron stars. And so there is certainly overlap between sort of experimental stuff that is happening here, or will happen here, with actually observations that we do of neutron stars. Ultimately, one wants to try and determine the equation of state of the ultra-dense matter in a neutron star. So we want to determine the pressure density curve, but of course we don't directly observe that. What we actually observe is the mass-radius relation. So what you can do is to try and measure the radius of a neutron star for a given mass, or ultimately you want to try and narrow down all these possible equations of state to find out exactly where you are located on this diagram. You could do this with measuring masses and radii, And one other thing you can do is by looking at the cooling of the star, right? Because the cooling depends exactly on what the structure and what the composition of the material inside the neutron star is. So observationally, these are the things that we need to go after to try and constrain the equation of state of ultra-dense matter. So neutron stars are interesting. How we go about observing them then? We can see these in multiple places throughout the universe, of course. The youngest ones we know of are those that are formed in supernovae explosions. Here is the Crab Nebula. And as you look at the very, very center, you zoom down to about 1.6 arc minutes across here. This is 8 arc minutes to give you an idea of the comparison of the size. You see the neutron star there, but you also see this swirling, extremely hot million-degree gas. So these are particularly interesting if you want to understand about how these wind nebulae form, how the magnetic fields of the neutron star interact with this region. But in terms of actually trying to understand exactly what the structure of neutron stars are, this is a hard place to do it because you really have the pulsar wind nebula in the way that you have to understand too. One of the best places to study them are actually isolated neutron stars. These are neutron stars where the supernova remnant and the pulsar wind nebula are faded away. These are a lot older. These are optically very faint, but X-ray bright. Their temperatures are around about 10 to the 6 Kelvin. But we know of very few of these. These are actually particularly hard to find. So while these are actually a brilliant place to study neutron stars, we don't know of very many of them. And so we need to find other places to study neutron stars in addition. Pulsars themselves, so these are rapidly rotating neutron stars that emit regular pulses. These are some of the best clocks. These are the best clocks in the universe. They're a great place to study neutron stars because you can use their very accurate timing information to be able to, for instance, measure the mass of these objects to extremely high precision. Here's a very nice example from a few years ago now of the most massive neutron star, around about 2 solar masses. This is a binary system that has both a neutron star and a white dwarf in there. And it's aligned just so that that the pulse beam actually passes straight past the white dwarf. And when this happens, what you see in the time it takes the pulse to arrive to you, you find that the pulse is slowed down a little bit because of the traveling through the gravitational field of the white dwarf. And so you actually get Shapiro delay because of this, right? A gravitational, general relativistic effect. And this is what you see in the timing residuals here. This peak here is because of that Shapiro delay, and that actually allows you to get extremely accurate measure of the masses in the binary system here. And so this is a great, pulsars are a beautiful way of being able to determine the masses of these neutron stars. And by measuring, say, a 2 solar mass object like here, you're already able to rule out some types of equations of state. The problem is actually hard to get the radii of neutron stars in these binary systems. And so you get constraints this way along this mass radius diagram, but you don't have any constraints this way, right? And so again, you want to try and really be able to get multiple, both mass and radius constraints if possible. And so that leads me to talk about X-ray binary systems, which are some of the brightest X-ray sources in our own galaxy. So there are plenty of them. We know of many of them. And because they're bright, we can get great signal from them. These are binary systems where you have a companion star that's typically about the mass of the sun or less. That's orbiting around either a neutron star or a black hole. I'll talk exclusively about X-ray binaries with neutron stars in today. And there are an evolutionary phase where the companion star fills its Roche lobe, which is its gravitational sphere of influence. And that allows mass to transfer from the companion star to the gravitational sphere of influence of the neutron star, and it can accrete down onto the surface. When they're actively accreting, these are, as I said, some of the brightest X-ray sources in the sky. And this process of the material accreting down onto the neutron star converts gravitational potential energy into radiation. And so these, the disk of this disk is extremely hot and is extremely bright in X-rays. So when these things are in outburst, when there's material actively accreting onto the neutron star, they are extremely bright. But studying the neutron star itself then relies on looking only at when we see an event called a type 1 X-ray burst, when you actually see nuclear burning happening on the surface of the neutron star. You're complicated from an outburst by the fact that the accretion disk is emitting most of the light and not the neutron star. If you want to see primarily X-rays from the neutron star itself, you have to wait till they go into a phase that we're called quiescence, and this is where the rate of material accreting onto the surface drops dramatically, and these things become a lot fainter. And when we look in quiescence, we see predominantly thermal emission from the neutron star surface itself. So the neutron star in the center is hot, around about 1,000,000 degrees Kelvin. And so we see a quasi-black body spectrum coming from the neutron star itself. And so we can actually study the neutron star in these systems. Why are these neutron stars hot? These are actually low mass X-ray binaries are old systems. They've evolved significantly. And the neutron star, if left to its own devices, would have cooled down by this point. We actually find that they're still hot, and so there must be something going on that keeps them hot. And that's the fact that we're getting this accretion down onto the surface. These repeated accretion outbursts inject energy onto the neutron star. And as you accrete material onto the surface, you compress the crust. As you compress the crust, it causes electron captures in the outer part of the crust at a depth of around about 200 meters. And it also causes picnonuclear fusion to happen deeper in the crust at depths of around about 400 meters. And these together impart something like 2 MeV per nucleon accreted onto the surface. So this injects energy into the neutron star and keeps it hot, and over repeated outbursts, timescales something like 10 to the 4 or 10 to the 5 years, you get into a thermal equilibrium where the core is kept warm by the accretion during the outburst period and cools off slightly during quiescence. The energy input is from the material accreting onto the surface, and that then driving the nuclear reactions in the crust. And so how bright these things are in quiescence is set by the time averaged accretion rate onto the surface. So the amount of material you're dumping onto the surface averaged over 10 to the 5 years or so. So here is an X-ray spectrum of one of these objects in quiescence. This is X-ray count rate versus energy here. This is in detector space. So this thing that we call the power law is curved simply because the response of the detector is not the same at all energies. And also because there is absorption due to gas in our own galaxy at lower energies. But you can see the X-ray spectrum is dominated by this black body-like component here, right? This is behaves just like a black body, so its brightness is proportional to the radius over the distance squared and the temperature to the power 4, right? So you can actually get constraints on the radius of the object just by modeling the thermal spectrum of these objects, right? The spectrum is not quite a black body, however. It actually depends on the structure of the neutron star atmosphere, and that's because in the atmosphere, the hotter photons, the opacity is highly energy dependent, and so the hotter photons come from deeper down, and so your spectrum is slightly harder, has slightly more higher energy photons than a typical black body. But it behaves just like a black body, and by modeling it, you can actually get a radius measurement for these objects. If you have a high enough signal to noise, You could even get joint mass radius constraints too. People have looked at trying to do this in the future with much higher collecting area X-ray telescopes than we currently have. So these are a very promising place to study to be able to get mass radius constraints on neutron stars. I said these things are in transient objects. They go through these cycles of actively accreting onto the surface and then being in a quiescent state where there's very little accretion going on. And these transients show a very wide variety of types of behavior. This is the count rate here versus time. This is about a period of 10 years. Yes?
Yeah, so when you do this very often, you assume that the atmosphere is hydrogen. But you're adding in X-ray bursts. So what about turbulence, dredging up some of the other stuff like?
So there are models for helium and carbon atmospheres too. The carbon atmosphere looks quite different from what we see in quiescent neutron stars. The helium atmosphere is not so different from the hydrogen atmosphere and certainly at the signal to noise that we have right now, you can't distinguish between the two. You certainly could, so you can certainly model these things and add these in, right? Sure. You can, so you can always change the model you fit to the data and see how that, what systematic effects that gives you on the radius measurement, right? I would say so far, the constraints you get from getting the radius measurement on these sorts of data, you're not at the stage where you have to worry so much about the differences between the models, I don't think. I think you will do at some point, right? Certainly when you get a much higher count rates. Okay, so more about these sorts of transients. So these go through these outbursts of and quiescent cycles, and they show a wide variety of different types of behavior. The outbursts typically last weeks to months and recur on timescales of years to decades, but individual sources look quite different. So for instance, this one object here has one outburst over a 10-year period. That outburst lasted about 2 months. This object here has an outburst a year or more in this 10-year period. This object at the bottom has an outburst that lasts about 2.5 years. And it's these objects with these extra long outbursts that first started an interest in looking for objects where the crust may get particularly heated by the accretion event. Right? So if you have a particularly long accretion event, you can actually heat up the crust significantly out of thermal equilibrium with the rest of the star. And then you can hope that over the following years, by monitoring these objects, you can see the cooling of the crust itself, right? And so back in 2001, 2 objects, KS1731 and MXP1659, both had been in outbursts for a long time. 1731 had been in outbursts for 12.5 years. 1659 had been in outbursts for 2.5 years. And so it was thought that these should be significantly out of thermal equilibrium, the crust should be significantly out of thermal equilibrium. And so these would be the great places to see whether we can actually see the crust cool, right? So we went and started doing this, first led by Rudy Vinans and then by myself. We looked at, we monitored these objects with Chandra and XMM Newton over several years, and we saw the crust cooling, right? So we see the quiescent spectrum, we model it to get the temperature out, and we see the dramatic increase over the first few years. So this is time since the end of the outburst, so time it's been in quiescence. This is the temperature. You can see that 1659 drops by a factor of 2 in about 2 years in temperature, and 1731 drops by again, a factor of 2, or a little less than a factor of 2, and again in just a couple of years. So they have thermal relaxation times, e-folding times of 400, 500 days, right? So these things actually cool quite rapidly compared to what people thought they would cool at the time. Now, many years later, 10 years later since we first started getting these results out, there have been many more of these objects seen. And we've not just been looking at objects that have been in outbursts for several years. We've started looking at objects where they've been in only outbursts for a few months. And surprisingly, we've been finding even in some of those objects that those crusts are hot, and we actually see them cool also. So here's a compilation done by Jeroen Homan of 6 of these objects. There's actually 9 objects now where we see this cooling happen. You can see that there's a wide variety of initial temperatures for the crust. They all show the same general trend, that they cool rapidly over the first few hundred days, and then typically tend to, those that we've monitored long enough have started to sort of flatten off at the end. They don't all require having extremely long outbursts. But this gives us a beautiful set of data that we can start testing models for the crust, right? And ask what sort of properties do we require of the crust to be able to reproduce the cooling that we see in these objects. So what does it tell us about crust properties? Well, first it tells us that there is a crust, right? There must be something there that gets heated up that then cools down for us to see this. And so it actually nicely shows us that the crust is there in these objects. But what else can it tell us about crust properties? I like showing this example here this is ancient now, this is from 2002, but it's kind of a nice, gives you a nice feel for how some basic properties of the crust change how you might expect the cooling curve to look. So here are 4 different cooling curves. The top 2 lines here, these solid line and the dotted line, for a crust that has a low thermal conductivity. The difference between the 2 curves is that one has a core with standard cooling, and one has a core that's allowed to have enhanced levels of neutrino cooling. And then these bottom 2 lines, the dashed curve and the dot dashed curve, have a high thermal conductivity, and again have a standard cooling in the core and enhanced cooling in the core, right? So it just gives you a feel for how these curves might depend on some basic properties for the crust and the core of the neutron star. Here's the very first observation of KS 1731 plotted on top. And what we can do is reveal where the data lie, right? And you can already see it tells you it doesn't look anything like these top 2 curves that have a crust with a low thermal conductivity. So it's actually cooling a lot quicker than some people have predicted. And it also shows you to get these sorts of temperatures, you may require enhanced levels of neutrino emission in the core, at least based on these initial calculations. Yeah. Crusting cools the inner crust. Yeah. The core will take a significant fraction of the heat flux, right? The temperature gradient actually takes most of the heat towards the core, right? But the thermal time scale for heating the core up is 10 to the 4 or 10 to the 5 years. So what we see as the time progresses is the heat from deep in the crust diffusing outwards, right? And so the shape of this cooling curve actually tells us about the shape of the temperature gradient inside the crust itself.
Does the ongoing accretion and quiescence have any impact on any of these?
I'm going to get to this at the end, don't worry. Yeah.
So
Is most of the heat in the inner crust? Yes, the temperature profile peaks in the inner crust, I believe. Or isn't that right, Ed? If I remember rightly. Yeah. Yeah. You're asking me, you're telling me. I'll talk a little bit about what sets the thermal conductivity in a minute. Okay. So these sorts of observations motivated Ed and Andrew Cumming and others to try and start doing more quantitative models for what the crust should look like. This is some examples from Ed's paper back in 2009, where they start to add in parameters for the crust that set how it cools. So for instance, you can set the outer temperature of the crust, so what it gets heated to at the end of the outburst, temperature of the core, so what that will set where the crust will cool down to at late times. The mass and radius actually sets how thick the crust is. A thinner crust will cool quicker, of course, right? And then one of the key parameters is the impurity parameter. So this actually gives you a measure of the range of charged nuclei in the crust. If you have a large range of nuclei, then you add lots of impurities into that structured lattice in the crust, and that will lower the thermal conductivity. If you have a very pure lattice, you'll have a much higher thermal conductivity, right? So this gives you some constraints on what the structure in the crust will be. Yeah, I'll show you in just a minute, actually. Yeah. One particularly strange thing that came out from this is that to be able to match the cooling curves at very early times, just a few tens of days after the end of the outburst, requires a mysterious heat source in the upper part, the outer part of the crust. And this is totally significant, right? This is around about 2 MeV per nucleon. This is the same amount of heat that's getting put in the inner crust from the density-driven fusion that's going on in the electron captures, right? This is a huge amount of energy that's mysteriously coming from somewhere that's needed to be able to match these cooling curves. Should also note it's actually needed to be able to reproduce X-ray burst models too. These type 1 X-ray burst models require an extra heat flux in the outer crust too. So it seems to be something that's real. Yeah, that heat will diffuse quickly through the crust, right? And so we're talking here about way after type 1 X-ray bursts have finished, right? So the heat should have diffused through the crust, I would imagine, right?
It depends on the lattice structure and the build of the crust. It's like closer to baking and cooking at that point in time. You have an inner heat and then an outer heat. Well, you expect if you have this huge turkey, 15-pound turkey covered with aluminum, a thick with aluminum foil, you're going to have an inner. If you decide to, if there's some big heat that comes out from the outside or comes from the outside towards the turkey well, then you got on the other side of the aluminum foil. It all depends on that lattice and the characteristics of that lattice, because we're now moving to material science. Material science has a whole new dimension of questions.
No, agreed. But in terms of the X-ray burst, to actually just ignite the X-ray bursts themselves requires that extra heat, right?
But during the burst itself, you run out really high temperature really quickly. So it is very much like adding a heat source on the outside of the neutron source or breaking period of time.
Agreed.
The burst itself
Yeah.
is hot.
Yes. Right.
Okay. Sorry.
No, that's right. That's okay. Okay, so this tells us that to be able to get these high thermal conductivity, you actually need quite a relatively low impurity parameter, which tells you must have quite a regular lattice. Molecular dynamics simulations by people like Chuck Horowitz give us some ideas what these things may look like. Here is an example from one of his papers, where the blue are the atomic nuclei of all the same charge, and the red are the impurities, right? And you can see that they sit in between the regular lattice structure, and that will act to lower the thermal conductivity. Also from these molecular dynamics type of simulations, one can learn about deeper in the crust. And what happens deeper in the crust is that you expect that the nuclei get distorted at these extremely high densities and what gets termed nuclear pasta, right? And so you expect the interface between the crust and the core that you get these, you can get all these weird types of shape of structures coming in the crust. So you know, the gnocchi, spaghetti, lasagna, right? These all happen. All these potential things come out of the molecular dynamics type of simulations that Horowitz and others do. These, of course, will not be good thermal conductors, right? And should actually act to like a blanket, right, and keep the crust hot. And so the presence should be, we should be able to see the presence of this nuclear pasta in the cooling curves, right? It should change the thermal gradient in the crust. So we can actually try and test whether this sort of nuclear pasta is actually present in the crust by looking at the cooling curves. So this is talking about KS 1731. A couple of years ago, we got one more Chandra observation of this object. We've now been looking at it 14.5 years since it went into quiescence. Up until that point, again, this is temperature versus time. It had been cooling nicely following a power law. And this blue line just shows you the fit to the earlier data. And you see we expect it to keep on going down. And our observation, latest observation here, taken 14.5 years into quiescence, showed that it had remained exactly the same temperature. So the 2009 temperature was 64.5 EV, and in 2015 we got 64.4 EV2. The spectrum also look identical. There's no change in spectral shape. It certainly seems that the temperature has remained the same. And if you just ask how many sigma away from this extrapolation, this data point is it's about 3.5 sigma away from continued cooling. So it seems that cooling has stopped in this object. So to get some better idea of the constraints that we can get on the crust properties, we went about using Ed Brown's neutron star thermal evolution code, D star, to try and figure out what's the sensitivity of this cooling curve on certain parameters for the crust. So we, again, looked at the core temperature, the impurity parameter, and the shallow heating. And then we also added an extra set of models testing the presence of nuclear pasta. And there you can test the density where you get this transition to having nuclear pasta, and also what the impurity parameter of that pasta is, so how good a thermal conductor it is. There's a whole bunch of other parameters that get fixed in this model. I've just put them there for the aficionados who care about what those things are. You don't have to worry about them. Changing some of these things can make an impact. We didn't explore what it does here. To give you a bit more of an intuitive feel as for how each of these parameters changes these cooling curves, here we have, again, the temperature versus time. And in each of these plots, we just changed the parameter, just one of the parameters. The solid line is the best fit that we get to the data. The dashed line, the blue dashed line here, when you have you lower that parameter value, and the dotted line is when you increase that parameter value. So if you look at the core temperature, as you lower the core temperature, of course, the temperature that the cooling curve ends up with is a lot colder. It's kind of obvious. As you change the impurity parameter of the crust, as you lower the impurity parameter, you make it a better thermal conductor, and so it cools more rapidly. If you have a higher impurity parameter, you expect the crust to be hotter at the beginning because, again, it's acted like because it's got the lower thermal conductivity, it's acting like a blanket. We also have this shallow heating parameter, and as you put the shallow heating in, it acts at depths close to the surface, and so if you increase the shallow heating, your temperature at early times increases, of course, right? And then how the pasta parameters make a difference. The impurity parameter for the pasta acts very similarly to the impurity parameter for the crust. As you increase the impurity parameter, you make it a have lower thermal conductivity, and so you'll end up with a slower cooling curve. As you change the transition density, if you move that transition density to, i.e. the location of where that pasta is, closer to the surface, then it acts like you have a blanket further out, and so that actually means that you end up with a slightly hotter neutron star to start with. Depends where you put the transition density, actually, right? It's a free parameter in our fits. We allow it to be wherever you want it to be, right? Yeah, I mean, the heat flow can't flow in more as easily, right? Yeah. So as when we fit these curves, we can get very nice fits to the data. Black is with no pasta, red is with the pasta. You see they're pretty much indistinguishable by eye, right? Whereas before we find that we have a low impurity parameter, we get some nice constraints on the temperature of the core. We require that there is shallow heating. In both cases, we require about 1.5 MeV per nucleon. But what we do find is that the pasta is not required to fit this cooling curve. And in fact, the models with the pasta actually force those values to be right at the extremes of the parameter range that we allow. In fact, it's saying that the pasta doesn't want to be there, right? So at least in the models that we do, it's actually saying that there's really no constraints on there being pasta, at least in the crust of this object. So just an example of how you can actually start to put some constraints on the properties of the crust in these objects. As I say, we now have 9 cooling curves from objects that we over the past 15 years. We have successful programs on Chandra and Swift to trigger on any object that goes into quiescence that's had a significant outburst that we can then that looks like a good candidate for following the crustal cooling. And so we, every year or every other year, we typically trigger one of these, and so we're slowly building up a good-sized sample of these objects, so we can start to probe the range of parameters of the crust of that we see in these objects. Okay, one of the complications, as Jay's question earlier suggested, is that in quiescence, quiescence isn't perfectly quiet, right? It's not that, it doesn't seem that accretion totally stops in quiescence, and this can, of course, can affect our results. So when you look at the spectrum of these neutron stars in quiescence, they often have not just a thermal component, but this power law component too. And that power law component is thought to be due to accretion onto the surface. In objects like KS1731 and MXP 1659, we don't detect the power law component, right? That may be a signal to noise, so it doesn't mean that it's not there, right? But in other objects, we do see the power law. It's there all the time. And in fact, we do see weird things happening. So for instance, here is XTJ1701. So again, it's temperature versus time. You can see it cooling, and then you can see it rapidly increases in temperature. One point is much higher than the others, right? Later here, when we started, this is once we started getting further monitoring, again, you see another burst happening, another increase, rapid flare happening in the quiescent flux. So what do we think is going on here? We actually think this is material making its way down onto the neutron star surface and accreting, right? So the question then is, how does this actually affect the crustal cooling that we observe, right? And so we really need to understand the power law and how accretion happens in quiescence to better understand any systematic effects it will have on modeling the crust. So we want to know how this power law component here affects the crustal cooling measurements. And again, another important thing is how it will affect the radius and mass measurements that you get from just modeling these spectra too. So how do we do this? Well, the best thing to do is to look at variability and look at objects that are typically brighter than some of these crustal cooling objects and see if we can understand what's going on. And there are some objects that we've monitored a lot in quiescence, and when we monitor them, we see a lot of variability, right? So Aquila X1 is a very well-known one. Its variability in quiescence has been suggested to either be the thermal component or be some combination of the absorption and the power law component, so it's not been very clear what's driving the variability there. But Cen X-4 has been a very nice one to study. This is one of the nearest neutron stars, and so it gives us some of the best signal to noise in terms of looking at these objects. And so even in a short 1 day long observation of Cen X-4, you can look at the variability on short timescales. So this is from a paper by Sergio Campana in 2004. Again, this is 1 day. You can see this thing is going nuts, right? It's varying like crazy. And so something is clearly happening during quiescence. So we went and studied this on a much longer time. We got all the archival data and some more. This is now a 20-year period on the shown on the baseline here, and you can see the flux is changing all the time. If we plotted the spectrum of the brightest state and the faintest state, right, you can see the spectra themselves look very similar, right? It looks like it's just a normalization offset, and that's exactly what the spectral fitting shows too. That the amount of flux that's in the black body thermal component is exactly the same in faint state and the bright state. And so this tells you that those two components are linked together, right? The power law component and the black body component are linked somehow. And it seems to be, the best guess is that it's driven by accretion onto the surface. Here's a little data plot with some extra points on. Again, you can see whatever time scale we look at, these things are varying wildly. You can look in a single observation too. This is now about 1 day. This is 80 kiloseconds. And you can see there's a flare here. And we can actually look at the properties of this flare. And you see that this is the hardness ratio that shows you that the X-ray spectrum doesn't change shape as this flare happens. So again, it's telling you that the thermal component and this power law component seem to be tied together. So we can ask a bunch of questions about what might be driving this, right? Are there any things in the crust that could actually be setting what's going on? Well, it simply can't be crustal cooling, right? This thing is not just some monotonic decrease. There are other things you can do in the crust. So you can have between X-ray bursts, you can change the amount of hydrogen and helium ashes in the crust. This should change the temperature, but it's expected to give a 20% increase over a period of 30 years. Again, not what we see. You can also have diffusive nuclear burning that could lead to a decrease in temperature over periods of years. But again, we don't just see a simple increase or decrease in temperature. So we're left with having to explain this by having accretion continuing in quiescence down onto the neutron star surface. So to look in more detail, we started a monitoring campaign with Swift. We monitored for 60 days and got 1 observation per day. And we saw that, again, it's wildly variable. Changes by a factor of 22 in just 2 days in terms of its flux. And we also see that the ultraviolet emission is highly correlated with the X-ray emission, right? So that also gives us some hints as to what's going on. Ultraviolet emission is certainly not coming from the neutron star surface itself. It's either coming from the accretion disk or from the companion star, right? So it tells you something about the accretion flow and not the neutron star. So the fact that the UV and the X-rays are correlated tells you that the accretion is really happening, right? Again, one can look at the spectral variability. This is the X-ray, soft X-ray flux versus hard X-ray flux. And it shows you that these things are linearly correlated. In other words, there aren't significant spectral changes in spectral shape as this thing varies, right? So again, this thermal component and this power law component are tied together as this thing varies up and down. We can look at the characteristics of the variability too. This is a structure function which basically shows it's a crude measure of the variability amplitude. It's a function of time scale. So this is 10 days and 100 days along here. The slope of this tells you about the process that you expect. The slope that we see here is consistent with red noise, which is exactly what you'd expect from sorts of processes you get from accretion onto the neutron star surface. And the fact that the X-rays and the UV are correlated, again, tells you that it's not just something that's happening down on the neutron star surface. You're getting emission from further out, either the outer part of the accretion disk or the companion star itself. And all this put together tells you that accretion does happen during quiescence. So this could seemingly be a big problem, right? The good thing is when you see accretion, when we see it in this Cen X-4 and Nuclear X-1, it's this highly stochastic variability. It's not ever a clear trend of a decrease in temperature as a function of time, right? When we look at these crustal cooling objects, we see that monotonic decrease in temperature, which leads us to strongly believe this is driven by crustal cooling rather than by accretion onto the surface. When you do see deviations from this, you do see those flares, right? Those flares typically don't last very long, and you find that the crustal cooling curve keeps on going exactly the same way as it was before, right? So those individual flaring events don't seem to be imparting a huge amount of flux onto the crust and affecting the cooling curve that we see. You can also ask the question, is Cen X-4 just an odd object? It's actually one of the brighter in terms of its luminosity and quiescent objects. And so we looked at a number of objects in the globular clusters, NGC 6440 and Terzen 5, to see what fraction are variable and what fraction show variability in their thermal component. And we found that only 2 out of the 9 quiescent neutron stars in those globular clusters showed variability in the thermal component. Again, making us believe that while accretion can happen in quiescence, it doesn't necessarily always happen, and it doesn't necessarily make a huge effect on the thermal component, though it clearly can do. So it's something that one has to bear in mind when looking at these crustal cooling curves, is that this can be an effect, but we believe that we can isolate periods when this actually happens. Okay, so we now see crustal cooling in about 9 sources, and we can actually start to observationally probe what's going on in the crust. And I think one of the things that's been shown from this that was really unexpected is this mysterious shallow heat source that sits around at the outer part of the crust and is imparting this approximately 2 MeV per nucleon accreted. And we still don't have a good explanation for why that needs to be there. And then in quiescence, you can see sporadic variability that certainly appears to be due to accretion. But at least in the cooling objects that we've seen, this doesn't so far make a significant change to the cooling curves, but it's something one has to always bear in mind when looking at these things. Okay, I'll stop there. Thank you.